All right, here's a second video that deals with 5.7 in your book. 5.7 talks about trig powers and partial fraction decomposition. It actually also has a third topic called trig substitution, but we're not going to worry about that because there's a way to get around that in future sections. At any rate, we started out dealing with trig powers in the last video, and in the last video we talked about what to do when you have an odd power, so sine to the third power of x, or cosine to the fifth power, or cosine to the third down here. In this video, we're going to talk about what if it's even instead of odd. And you're like, well, the odd stuff wasn't that bad. I just had to use this Pythagorean identity. And then stuff that I knew from U substitutions all seemed to work out pretty nicely. I like the odd ones. The even ones, got some bad news for you. They're miserable. They're not nearly as fun, I don't know if fun is the right word, as the odd power ones. But there's a way to do them, and I'll talk you through that way, and we'll learn how to do them, and then maybe we'll never talk about it again. So let's start out with the simplest example possible, the integral of sine squared x dx. The first comment is that you don't know how to figure out the antiderivative with this, and our Pythagorean identity wouldn't help at all, because our Pythagorean identity would change this into 1 minus cosine squared x, so we're not really getting anywhere. Turns out that we're going to have to go all the way back to a Math 112, a trig class, and take advantage of some identities. Maybe you remember these guys, these double angle formulas, that the cosine of twice an angle can be rewritten as twice the cosine of an angle minus 1, or 1 minus twice the sine of an angle. I don't know, at some point I bet you had to deal with these formulas. There's double angle sine, cosine, tangent formulas. And you probably had them memorized very briefly and could use them, and probably right now they look completely foreign to you. At any rate, whether you remember them or not, the cosine double angle formula had 3 different options, and 2 of those 3 options I have copied down here. And I don't need you to be an expert with double angle formulas. I just want to show where these formulas that we're going to get in this section come from. So what this gives me is a relationship between the cosine of twice an angle and the cosine squared of an angle. Cosine squared, even power here, we're going to end up using the fact that we can rewrite the cosine squared of some angle in terms of the cosine of some angle, which will allow us to reduce even powers to odd powers. Don't quite follow this yet? Okay, let me first take this equation that we have written here and solve it for cosine squared x. So add 1 to both sides of the equation and then divide both sides of the equation by 2. I'll trust that you can do that algebra, and I won't really go through all the steps, and we can see that cosine squared x is equal to this thing. Similarly, if we take the second line here, and this time we solve for sine squared x, so let's see, subtract 1 from both sides and then divide by 2. We get this equation. These two, think about these as formulas. You don't need to be able to derive these formulas. I just felt guilty starting out by being like, hey, these are formulas, trust me. These come from these double angle formulas, which at some point you accepted as true. And we can use those to come up with the 2 formulas we'll need for even trig powers. Good news, you don't have to memorize these. When we ever put anything like this on a quiz, I'll just be like, hint, and I'll give you exactly what's inside this red box right here. So don't think about this as something that comes to you for free. I don't want you to waste valuable space inside your head memorizing these formulas. I'll always provide them for you. And if you have them, this problem becomes almost trivial, right? If the sine squared x is just equal to 1/2 sine of 2x minus 1, this integral is just equal to this integral. And unlike this integral, this is an integral we can solve with just kind of our basic techniques. I guess we could take the 1/2 out in front of the entire thing, and then we could split this integral up into the sine of 2x dx minus 1 dx. Right? Note the 1/2 has to hit both of these terms, hence this outer layer of parentheses. And when we have the integral of a sum or difference of 2 different terms, we can break that up into the difference of those 2 integrals. What I'm saying is this line is equal to this line. And this line, I think we can figure this out. You can use a U substitution if you really want to, but I think you'll get to the point where you can do this without a U substitution. The U substitution that you could do here is you could let U equal 2x, and then what? du would equal 2 dx, so half of du would equal dx. You can go through all that logic, but I think you can also just think your way through this, right? The antiderivative of sine, well, negative cosine of 2x is going to be pretty close, right? The derivative of cosine of 2x, well, the derivative of cosine is negative sine, so this negative and the negative sign gets me back to positive sine. That's good. But what's wrong with this is if I took this derivative, I would get sine of 2x times 2, because I'd have to use the chain rule on this 2 right here. So what I need is a 1/2 out in front there to make sure that the derivative of this is the same as this. If you could follow those steps, go from here straight to here, great. If not, you can also do a U substitution if you prefer. For this one, my work is really easy. The antiderivative of 1 is just x. If I have all my parentheses closed, I believe I have the right answer right here. It's not a bad idea to clean this up just a little bit. 1/2 times 1/2 is 1/4. I could call this negative 1/4 cosine of 2x minus 1/2 x plus c, and then I can be done with this problem. The points that I want to make is the calculus wasn't too bad. Maybe I should have showed a little bit more work going from here to here. But the reason I didn't is if you can get to the point where you can do these u subs where the u is just a constant times your variable, if you can do those without actually writing out the u sub, they're so common that it'll save you a lot of time when you're going through these in your work. So you might want to get to the point where you can do this without this u sub. At any rate, if you can get past that minor little difficulty and you have this formula given to you, there's not a whole lot to this problem. There's not a whole lot that's good news that makes it kind of easy. There's not a whole lot that's bad news. It makes it kind of boring. You don't really do anything here. There's not even the clever save one of them for a u substitution later that we saw with the odd trig powers. When you have even trig powers, frankly, I just don't like them that much. I don't think they're that much fun, so don't expect to see a whole lot of them. However, we do need to consider a couple other cases, so let's do a couple more examples. What if instead of my power being a 2, it was a 4? It's still an even number, but now it's a bigger number. I switched from sines to cosines just to kind of mix it up, but what you'll see is it doesn't really matter whether it's sine or cosine. It's just going to determine which of these two formulas that you end up using. At any rate, if you started out with this problem, the trick that you'll do will be pretty similar to the trick that we saw in the previous video when we had a cosine to the 4th power. We rewrote it as cosine squared squared. We're going to do the same thing down here. Cosine to the 4th of x is just cosine squared x squared. And the cosine squared x inside the parentheses, I can use this formula on. So I'll replace this cosine squared x with exactly what I see here. Be careful with your parentheses. 1/2, 1 plus cosine of 2x. And then note that this entire thing, including this 1/2, is being squared here because this entire cosine squared x was being squared up here. The problem is, this isn't something that we know how to integrate. Right? But we can simplify this a little bit, and it'll reduce to a case that we can almost integrate, and the little part that won't integrate, well, we'll have a method for dealing with that. So if you stare at this and try to get rid of all the parentheses to clean stuff up, remember all this stuff is being squared. So the 1/2 squared gives me 1/4, and since the 1/4 is just a constant, I can pull it out in front of the integral. And then I also have 1 plus cosine of 2x being squared. So think about FOIL, 1 plus cosine of 2x times 1 plus cosine of 2x. We'd end up with 1 plus 2 of the cosine 2x things plus 1 of the cosine squared 2x things. That would get me here. You're like, oh, this is good news. In Calculus 2, you like it when you have a sum of multiple terms because you can just integrate each term individually. Figure out the antiderivative of 1, that's super easy. Figure out the antiderivative of 2 times the cosine of 2x. That's pretty easy. We did something very similar up here. You could use a u substitution, or if you're clever, you can get away with not using a u substitution. The one that causes trouble is this guy. Cosine squared 2x. I don't want to deal with that. Yeah, I don't want to deal with it either. You don't know how to figure out the antiderivative immediately. However, you do have a formula that'll work. Right? I mean, if you could figure out sine squared x, it makes sense that you could figure out cosine squared 2x, it turns out. If you can do sine squared, you can do cosine squared. Won't be that much harder. We'll just have to go through another iteration of this stuff. So I'll leave everything from this line completely alone, except instead of writing cosine squared 2x, I'll come back up to these formulas, which again, you don't have to have memorized, and replace it with 1/2 times 1 plus cosine of twice my argument. So when my argument is just x, I change it into a 2x. Well, what if your argument is a 2x? If this were a 2x here, well then I would want twice this 2x, I'd want 4x. What I'm saying is that cosine squared 2x using those formulas above can be rewritten as 1/2 times 1 plus cosine of 4x. And what I have here isn't the prettiest thing in the world, but what I have here is something we can integrate. Before I do this step of finding the antiderivative, let's get rid of these parentheses. That always makes life easier. Take the 1/2 and distribute it through. That gives me 1/2 plus 1/2 cosine of 4x. And while you probably could integrate at this point, figure out antiderivatives, I'm not going to. My personal preference is I like to clean things up as much as possible before I figure out antiderivatives, because for me it's more likely I'll mess up an antiderivative than it is that I'll mess up some algebra cleaning something up. So what I'm saying is this 1 and this 1/2 could be rewritten as 3/2. And then these coefficients of 2 and 1/2 can be pulled out in front of their respective integrals if I distribute this integral to each of my different terms. So being really careful with my parentheses, I can rewrite this as this integral. So note the 1/4 is going to hit everything because of this outermost layer of parentheses. And then the integral hits each of the different terms. So the integral of the 3/2, the integral of this term, but the 2 can come out in front of the integral. And then the integral of this term, but the 1/2 can come out in front of the integral. I think I've done about as much as I can to make my calculus work easy to figure out the antiderivative of this mess. Let's see, the 1/4 will leave it alone. The antiderivative of this 3/2 here would be 3/2 x. The antiderivative of this next term will leave our constant of 2 alone, and then think about the antiderivative of cosine of 2x. You could use a u substitution if you want, but I think you can talk yourself into it. The derivative of sine of something is cosine of something, so I'm going to almost put sine of 2x right here. But then I'm going to think about, well, if I took the derivative of sine of 2x, I'd get cosine of 2x, but I'd also get an extra 2 from the chain rule, the derivative of 2x. So to make sure that I don't get an extra 2 up here, I'm going to need a 1/2 down here. So I'll have 1/2 sine of 2x, and then this 2 ends up being this 2. In case you didn't follow that, we're going to do essentially the exact same steps over here. We're going to think about, all right, cosine of 4x, that's almost sine of 4x, but not quite, because if I took the derivative of sine of 4x, I'd get cosine of 4x times 4. And I don't want cosine of 4x times 4, I just want cosine of 4x. I better put in a 1/4 right here to make sure that all the pieces match up. I'll close these parentheses so the 1/4 hits everything, and then tack on my plus c. And this is a perfectly acceptable answer the way it's written, but as you probably know by now, I like making things pretty. So 1/4 times 3/2 is the same as 3/8 x. This next term, the 2 and the 1/2 cancel out, so this is just sine of 2x, but don't forget to make the 1/2 hit it. Sorry, 1/4 hit it, so you get 1/4 sine of 2x. And then this term, a half times a fourth is an eighth, and an eighth times a fourth is a 32nd. So I get 1/32 sine of 4x. And then don't forget your plus c. As you can see, these get kind of annoying when the power, the even power here is anything bigger than 2. But you can deal with it. It's just multiple iterations of the same thing. You'll have to use this formula multiple times. One last example. As we saw in the previous video, sometimes you'll have a product of sines and cosines raised up to powers. And as we talked about in the previous video, as long as one or the other is odd, we can make our odd trick, which most people like a lot better, work out. But you might wonder, what if they're both even? What if you had like sine squared times cosine to the 4th power? How would you possibly deal with that? Well, the trick is we can use our Pythagorean identity to make them all the same type, right? To make them all cosines. So I could rewrite sine squared x as 1 minus cosine squared x. And now 1 minus cosine squared x times cosine to the 4th x, I can distribute this and get that this is cosine to the 4th x minus cosine to the 6th x dx. The integral of a sum or difference is just the sum or difference of the two different integrals. Essentially what I'm saying is this is just two different problems. Figure out cosine to the 4th x, figure out cosine to the 6th x. If I'm being perfectly honest with you, I don't want to do that. The good news is I don't really have to, because cosine to the 4th x we've already done right here, right? So I already know that the integral of cosine to the 4th x is this mess down here. So if I could just figure out cosine to the 6th x, I'd be in good shape. So maybe I can solve cosine to the 6th x down here, and then we can take this answer in green and subtract the answer that I get here in red and call that good. Cosine to the 6th x, kind of like cosine to the 4th x when we thought about it as cosine squared. Cosine to the 6th x, we can think about as cosine squared cubed. When you have exponents raised up to exponents, you multiply together the two exponents, and 2 times 3 gives me this 6. But note that I want the 2 to be down here in the parentheses because cosine squared x is something that I have a formula for. This is going to be miserable. I don't even know if I'm going to finish this. Be really careful with your parentheses. We want the 1/2 to be multiplied by 1 plus cosine of 2x, but then we want that entire 1/2 and 1 plus cosine of 2x to be cubed, and then we want the integral of that entire thing. It's just a parenthesis nightmare. What we're going to do now is get rid of some parentheses. The 1/2, in addition to this 1 plus cosine of 2x, is all cubed. So let's first cube the 1/2. 1/2 to the 3rd power is 1/8. I can take that 1/8 out in front of the integral. And then 1 plus cosine of 2x cubed. I think what we're forced to do is just expand that out. Expanding cubics is so ugly that I did it in two different steps. Took the 1/8 down in front in this first step, and then 1 plus cosine of 2x to the third power. Think FOIL and then FOIL again. I think if you do all that and combine all the like terms, you'll get this disaster down here. 1 plus 3 cosine of 2x plus 3 cosine squared of 2x plus cosine to the third power of 2x. I'm already regretting doing this example. The good news is that a lot of these terms aren't bad, right? The bad news is that one of these terms is going to be miserable, but I think we can kind of check off a lot of them and maybe not even finish this example, right? The antiderivative of 1, that's easy. All right, that's just going to be x. The antiderivative of 3 cosine of 2x, the 3 is just a constant, and the antiderivative of cosine of 2x, we've done that a few times already. It's similar to this step where you could do a u substitution or you could just figure it out. I think we're good on this one as well. 3 times cosine squared 2x. That looks horrible, but you could take the 3 out in front, and then you'd have cosine squared 2x, and we know how to deal with things like cosine squareds. In fact, I think we've done cosine squared of 2x. If I could just find it, here it is. Cosine squared of 2x. We've done that one already too. Finally, cosine cubed of 2x. That looks bad. Third power seems worse than second power, but it's not. The nice thing about third power is it's odd. And when you have odd powers, they work out a lot better. You could follow the methods that we did in, I guess, this first example and do something really similar to figure out this guy here. So you could do each of these 4 things. I'm not even going to do them for you, but in theory, you could do each of these 4. And then you could take this 1/8 and distribute it through. And you're like, whoo, that would be miserable, but at least then I'd be done. Well, no, that's this thing in red. Remember, the thing in green here needs to be part of your answer as well. So you take this answer and you'd subtract the answer that you got over here, and then eventually you'd be done with this problem. I think I'm going to call that good. I'm going to say that we've seen the pieces for all of these at some point in these videos, and rather than make some 20-minute video just finishing one example, I'm going to call that good and hope that you've gotten kind of the spirit of these examples and you realized, wow, that would be miserable. It could be done, but I bet he'll never test me on a problem like this. And if that's your thought, you're 100% right. I never would. I think this is the extra credit problem on the homework. So if you want to do it for extra credit, feel free. And if you don't, call it good. And let's end trig powers right here.